Hello, my name is Jordan Smith, and today I will be talking to you about porosity, one of the most important properties of petroleum engineering. So first start off, talk about porosity, you have to first know how they could describe a pore. And this could be this, and you have rocks in here, like this. And so this empty space in between the rocks, like this, are all considered pores. Now, the important thing about porosity is packing. The looser the packing of the rocks, the higher the porosity. The tighter the packing, the lower the porosity. Now, if you have the rounder rocks, will always give the looser packing because they're only touching at corners, so it leaves the most amount of pore space. But if you were to have flatter rocks, they would fit together more closely and therefore have less pore space. So rounder rocks will maximize the amount of pore space available. But one reason why porosity is one of the most important things in petroleum engineering is you can measure the amount of pore space and determine the amount of volume of hydrocarbons within the rocks or a group of rocks. Now, we can, for porosity, things with the same packing, volume, and shape will always have the same porosity. So if we were to have a diagram with rocks all spherical, large spheres, or all spheres all within the same size container, medium spheres, but packed the same way in the same space of volume, or even tiny spheres, all packed the same way in the same volume, they would all have the same porosity. In an equation, porosity can be described as the volume of the pores um, compared to the volume of the total bulk group of rocks. So, and the bulk group of rocks is just the volume that the rocks together contain. So, in an equation, as an example, it can be described as this. Let's say you have 300 milliliters of rocks in one container, and you were to take a 200 milliliter beaker of water and fill into the container until you were to fill it up to the top, and there was 80 milliliters left in the beaker, then that means we used 120 milliliters of water, and that would be the pore volume space, 120 milliliters of water, or 120 milliliters. You would take that and plug it into the equation and put the bulk volume of the entire rocks over, give you 2/5, and your porosity will be described as 40%. Um, and this clearly shows that porosity is the ratio of pore space to bulk rock space. Thank you.
Hello, my name is Reed Michelson. I'm the third member of this group in this petroleum engineering introduction. And the third topic that we decided to investigate in the industry is the concept known as permeability. Basically, in its most simple definition, permeability is a number we use to represent how well a given fluid can flow through a given porous medium. So, for example, a sponge that has water being poured over it, a sponge would be very permeable because water just flows right through it. But if I took, let's say, a marble or something, or to be more realistic, how about a very dense volcanic rock? If I poured water on that, it wouldn't be very permeable. It would just slide right off. And essentially, we went into the history of permeability and found that it was first quantified by a person named Henry Darcy. Henry Darcy first quantified it with a very simple experiment where he took columns of loose sand, like you would find at the beach, and he flowed water through it. And it didn't have any applied pressure other than the pressure of the atmosphere on top. It was as if you filled a graduated cylinder with sand and then poured water through it. And he found a slightly longer definition of permeability than what I'm going to give here, but let's see how that looks. Yes. We, after rearranging his definition of permeability, find that permeability K is basically equal. It is equal theoretically, but it's not always perfect in real life. But permeability for a given fluid and a given block of material is equal to the flow rate of that substance times the length that it travels down, the length of the medium times the viscosity of that substance divided by the pressure gradient from end to end of the medium, and then further again divided by the cross-sectional area that the fluid is flowing through. So K is permeability, Q is flow rate, mu is viscosity, L is length, A is area, and then delta P is the pressure differential. I'm not going to go into the units here because I can't recall all of them off the top of my head, but K is commonly in units of Darcy, named after Henry Darcy, obviously. With real rocks, we don't use Darcy's unless it is basically too good to be true. Most rocks have 0.00 something Darcy's, so we simply use millidarcies. To visualize it, let's draw a quick example. This is the area. A fluid flows in from one end, out from the other. Here we have pressure 1, pressure 2, and then from end to end we have delta P. It doesn't make sense, obviously, to try to show you where viscosity is. But, and then Q is here. So a fluid flows into one end of the sample, is distributed across a certain area, this cross-sectional area. It is pushed and pulled by this pressure differential from one end of the sample to the other. It flows down a certain length and it has a viscosity. And to show you how we would want permeability, let's look at it this way. A rock that is very permeable, oil will flow very quickly through. We cannot measure permeability. It is not an actual property of the rock that you can get by measurement. You have to measure these things and calculate permeability. People commonly just say we measure permeability with software that automatically computes this for every trial run. But if we want a reservoir rock to have very high perm, we would want a high flow rate. Well, for the purposes of money, we want very thick oil. Thicker oil, more viscous, is denser oil. Denser oil has a higher energy density. We get more energy when we burn it. It is more valuable to us. It's more expensive. We can sell it for more. It is a more valuable product. So we automatically, ideally, we would want viscosity to be very high. And then for a very permeable rock with that viscous fluid, we would want a high flow rate so that we can produce it faster. We would want a long length and a small surface area. Those things will affect the flow rate greatly. And then we would want a very small pressure differential. A number of reasons we would want a small pressure differential is because abrupt processes tend to ruin equipment faster. They tend to be more dangerous and they are less reversible. They are simply harder to work with than slow stepwise processes. And permeability, after all this, permeability is basically the holy grail of all concepts that petroleum engineers might face. It is just as, if not more important to us as engineers and for economic purposes as porosity. You cannot have permeability without porosity, obviously, but a more permeable rock means we can get oil out of it much more easily. It also means we can inject fluid much more easily if we want to inject water or steam or natural gas to aid in creating a desirable pressure differential for the purpose of getting out more oil. It is an extremely, extremely important quantity. And currently, right now, we still do not have very, very good correlations with, we have not proven very good correlations between permeability and as many of the rock's intrinsic properties that we would like. Because to measure perm as accurately as possible, you need to actually take a rock out of the ground and run flow rate tests on it. You have to account for all these variables and you have to do the testing yourself. That can be extremely expensive, very, very expensive, costing hundreds and hundreds of thousands of dollars. So a big focus of current research right now is actually to do tests under different kinds of conditions with new novel ideas in order to try and show that there might be some correlation between permeability and, say, something like resistivity or grain size or grain sorting or clay content or silt content or say neutron density, anything, gamma rays. There are a lot of properties that we can measure more easily from the surface without actually penetrating the ground. And if we had a good correlation, we could get a good insight into how permeable a rock maybe is without ever having to take it out of the ground. and for obvious reasons, economic mostly, that would be extremely, extremely advantageous. That is a brief overview of permeability. Once again, it is extremely important. It is probably the most important thing that a petroleum engineer will ever learn. It is used in every single class. It is used in basically every single job title within the industry. If you work in the oil industry, you know what permeability is and you know what it means when you see a high number or a low number. So that has been our presentation. We hope you enjoyed it. We're just going to end it here. Thank you again very much for all your time. We really appreciate it, and we hope you liked it.